Hello everyone, welcome back to chapter 24. A little bit of good news. I found a different power cord for my laptop, which is not producing all of the static that the other one was. So now I'll be able to make videos as long as I want, but I'll do my best to try to maintain a length of something between an hour and 75 minutes. If possible, at the maximum. But for our fourth video, we actually have quite a bit to cover, but I think the majority of the material is going to go fairly fast. Now we've seen derivations for electric potential for individual particles. We went through the dipole derivation in the last video, along with the line of charge. So now we need to look at things like a ring of charge, a disk, and then expand into things like spheres and cylinders and see what kind of potentials those are going to produce. And then we'll be at the end of the chapter, and we can take that knowledge and start applying it into the circuits, which is a lot more fun, believe me. So next thing we want is to look at the electric potential that is going to be produced by a ring of charge. So we'll draw a ring. We'll put some charge on that ring. Our ring will have uniform charge distribution, just like every other scenario. And what this means is, just like the line of charge, there will be a certain amount of charge per unit length as we go around this circle. And the last time we discussed a ring, we called the infinitesimal length of each segment ds, but this was still a charge per unit length ratio, so we can still call this lambda. And because of our uniform charge distribution, regardless of the sample size of charge, we have to have the same ratio. So if we let big Q be the total charge of the ring versus the total length of the ring, which would just be the circumference, that's the same lambda value. We will give the ring a radius of big R, and we'll go to measure the electric potential at the midpoint directly above the ring, some distance of last time we called this Z, so we'll go ahead and stick with that notation. And then we need the measure of distance that each charge is from the point out in space where we want to measure. We will technically have an angle of theta here, but compared to the line of charge, everything in this right triangle that we've just drawn is constant. So we have no variable terms, which is really nice. But we do have to set up our integration to add up all of the individual electric potential values that each individual or infinitesimal amount of charge is going to produce. So in this case, little r is a constant. Every charge is the same distance away from the ring itself. And since the only thing that we have to integrate with respect to now is dq, the one thing that we do have to introduce into our integral is some information about how this charge has been distributed. And the way that that's going to happen is that we're going to say that dq is equal to lambda ds. So we have a quick substitution there. See, lambda can come out to the front, because that is a constant. Along with r, little r is a constant. The only thing that actually remains inside of our integral is ds. And so we'll integrate from some starting point, we'll call that 0, but then we have to go all the way around the circle, which has a circumference of 2 pi r. And that means when we evaluate our limit, we're going to get lambda 2 pi r over 4 pi epsilon little r. The 2 pi's will reduce with the 4 pi in the denominator. We now have lambda big R over 2 epsilon little r. And so technically this is the potential for the ring, a distance of z above the ring itself, except that we don't have z showing up anywhere in the expression. So what our author does, if you'll remember in previous videos, we said that for a laboratory setting, if you had to measure values of this right triangle, we have to have at least 2 measures so that we can solve for the other 2. So which 2 values would be the easiest to measure in a laboratory setting? And it would be these 2. R and theta can be solved for just by using basic trigonometry. And so r, which is the hypotenuse of that right triangle, would just be root of z squared big R squared. And so we're going to substitute that in. We have lambda r over 2 epsilon root z squared r squared. And the last thing that we're going to do with this expression, now that all the integration is done, now that we've added up all the charge throughout the entire length of the ring, we're going to come back up here and we're going to replace lambda with what it is. It is the charge per length ratio, but we're now talking about the entire ring. We have a total charge of Q. Oops, I wanted to go back to there. Q over 2 pi r. So that's our lambda value. And then we've got all this other stuff. So r 2 epsilon root z squared r squared. So the r's cancel, and we have our 4 pi epsilon naught, which is back. And then we have root z squared r squared. So there is the potential that is produced by the ring of charge. And it's at this point that we can play the what if game. Should be able to play the what if game with any kind of expression that you use. So what if we take this to certain extremes, like what if z goes to infinity? What's going to happen to the potential of the ring? Well, if z goes to infinity, our denominator goes to infinity, so potential goes to 0. In other words, you get too far away from this thing, you're not going to be able to register that the ring is there. You're just too far away from it to notice it. So what happens if the radius of the ring goes to infinity? Well, same story. If the radius goes to infinity, then the boundaries of the ring are so far away that you can't register them, and so we get a potential that goes to 0. What if your radius goes to 0? So what if you were to take that ring of charge and squeeze it down to a single point? Well, in that case, you would have a large collection of charge focused at a single point. Well, that should behave like a point charge then. So what happens to our expression if we let r go to 0? Well, if we let r go to 0, all we have left is root of z squared, or z. And so our potential goes to q over 4 pi epsilon z, which is the point charge expression. We've been using a little r for the point charge expression, but z is now the distance away from the charge collection that we're talking about. So that makes sense. That's what we want to happen. We want all of this to make sense, obviously. And then, let's see, the last thing we can try is to let z go to 0. Now, here's something interesting. When we discussed electric fields, when we considered the electric fields of the ring, we remember that all of these charges were sending their electric field lines towards the center of the ring, and because of the evil twin scenario, all of those field lines would cancel out, and we would get an electric field that was equal to 0 at the center of that ring. But that only happened because the electric field lines were vectors. Now we have a scalar quantity. Electric potential is a scalar. And so if we plug in 0 for z, then we end up with just r. And the electric potential at the center of that ring also behaves like a point charge expression. Because potential is not a vector, it really doesn't matter what direction the charge is from the point where we're trying to measure. All that matters is how far away the charge is. So for a ring of charge, I could have all of this charge spread out around the perimeter of the ring, like what we've been having, and I would get this value for the electric potential at the center of that ring. But I could just as easily take all of the charge from that ring and collect it and place it at a location a distance of r from that point, and I would get exactly the same electric potential value. So whether all the charge was located at a single point, or if all of that charge was spread out over a distance of r, the charge in the system is still a distance of r from the point. And because we're not dealing with vectors, the direction doesn't matter. So this is actually a very powerful outcome in terms of the math, because we can now take systems of, say, fractional circles. Maybe we have a half circle worth of charge, and we have charge spread out over the total length of that half circle, and I want to know what is the electric potential at the central radius value of that semicircle. Well, again, every one of these charges is the same distance of r from that point, and so the math makes no distinction between this being a semicircle or just a single point of charge that happens to be a distance of r. All I need to know is what is the total amount of charge that makes up that semicircle, and I need to place it all a distance of r from the point where we're trying to measure our electric field, and I'm going to get right back to a point charge expression. And so now we could take a system with multiple rings. Let's say R1, R2, R3. And R1, we can let that be 10 centimeters, and we'll say that that ring has 50 microcoulombs on it, positive. R2 can be 20 centimeters, and it has negative 75 microcoulombs. And then R3, charge 3, we'll say that has 100 microcoulombs on it, positive. And I'd like to know what is the electric potential that is being produced at the center of all of those rings. And we're assuming that all of the rings have the same center point. So to do this, we will add up the potentials that each ring is producing. But we now know that each ring has its respective charge, a distance of r away from the center. And so the potential that is produced by the first ring will be 1 over 4 pi Q1 over R1. Potential produced by the second ring, Q2 over R2. Potential produced by the third ring, Q3 over R3. We have 4 pi epsilon as a common term for each. We have 50 microcoulombs for charge 1. We've got 0.1 for R1, plus a negative 75, 10 to the minus 6 over 0.2, plus 100, 10 to the minus 6 over 0.3. From here, it's just a matter of crunching the numbers in our calculator, but this is it. This is all that is required. We've taken into consideration the charge that each ring has, and we've taken into consideration how far the charge on that ring is from the point where we're trying to measure. And that's all that electric potential requires. That's actually looking kind of messy, so I'm going to get rid of that. And I need a Q3 up here. Oops. So I'll go ahead and let you crunch those numbers if you want, and just see whether or not you get a positive or a negative electric potential at the center of that system. My guess is just because, we've got a lot more positive charge, it's going to come out positive, but I I won't jump to that conclusion until we've actually crunched those numbers. So a ring of charge, fairly straightforward. There really wasn't even any calculus that we had to do. All we had to do was add up the perimeter of our circular portion, and we were done. So for a semicircular portion, in this case we just had half a circle, but what if you have a portion of a charge segment or a ring that is not a full circle, but it's not a half circle. It's it's measured by the angle theta. Well, the length of where that charge has been distributed can be represented as an arc length. And since we've already been using S in the setup for all of our math, so we're going to go back up to the integration that we set up here. This was the integral that we set up, and we were integrating with respect to ds, but in this case it was for a full circle. So we're going to take that out, and we would just need to modify this for the angular displacement times the radius, and since arc length is equal to theta r, whatever theta is, we would go from the initial theta value, which would technically be 0 degrees, and then our final theta value would tell us, along with the radius of that arc length, what the final arc length value would be. One thing to keep in mind anytime you're using the arc length expression, your theta values do need to be in radians. So, pi over 2, pi over 3, pi over 4, whatever you need to do to convert your angles accordingly. And so, where did my semicircle go? There we go. So maybe we have an angle of 60 degrees here that we need to integrate, and I'm going to go ahead and bring that integral down here. We had 1 over 4 pi little r, which was actually this is just going to work out as r. It's z squared r squared 0 to pi r ds, and so that's going to collapse down to z squared r squared theta r. And from there we would just have to plug in an r value and a theta value, and then we say, well, z is equal to 0, because we're looking at a point that would be right in the center of that circular segment. We're not actually above it in any way. And so now we would get lambda theta r over 4 pi epsilon. Since z goes to 0, we just get r. We lose the r's. And so finally we get lambda theta 4 pi epsilon. And you can put lambda back in as the charge per unit length, but your charge per unit length is going to be based on theta r. So do keep that in mind. You're probably going to end up losing your theta value again in the process. All right. Moving on to the next topic of our discussion. Now we want to see what it takes to find the electric potential for a disk of charge. And that disk of charge, so we'll have a disk. We will have a uniform distribution of charge. That should always be the first thing for any of these derivations, is uniform charge distribution. We want to find the electric potential that is being produced directly above the center of that disk, some height of z above the disk. And just like the electric field derivation, we want to take this disk and we want to break it down into a system of concentric rings. And if we can find the potential produced by a ring, then we can add up all those rings and we'll get the potential of the full disk. Now our disk will have a full radius of r. And previously we would have measured the distance from our point in space to the collection of charges. And our collection of charges is going to be everything that's, you know, on the surface of this disk right here. And we would have called that R, but I want to reserve R to measure the infinitesimally changing radius. And so right here we would have a value of little r, but then the ring itself will have to have a certain infinitesimal thickness associated with it, and we're going to call that dr. And that means that the outer radius of the ring will have a value of r plus dr. So we have the inner radius, and we have the outer radius. And those values are going to be needed because the next thing that we'll have to do is figure out just how much area does this ring take up. So as we go all the way around this ring, I need to know how much area that ring is taking up, and then we'll have to add up all the areas of all the concentric rings until we get the full area of the disk. And this line of reasoning should also sound familiar because we used this same approach with the disk when we tried deriving the electric field. The amount of charge that is distributed about any area of this disk is what we called our surface charge density. We used sigma to describe this. And we could use the entire charge of the disk. I would call that big Q. And that would have to be distributed about the entire surface area of the disk, which would be pi big R squared. But we also have to be able to describe this as an infinitesimal sample. Doesn't matter what sample size we look at, whether it's the entire disk or maybe just a ring segment. So that ring segment would have some infinitesimal surface area, and it would contain some infinitesimal amount of charge. And that ratio will also have to be sigma. The great thing about this is that for every concentric ring that we use, each concentric ring is either going to be larger or smaller than all of the others. And for a larger ring segment, that means that we can hold a larger amount of charge, and vice versa. But we don't have to worry about keeping track of that because the ratio of the two needs to remain constant. So here we go. We're gonna set up our default expression for finding the electric potential. Now, the original point charge expression uses little r to measure the distance from the charge to the point in space where we're trying to measure. Since I'm using little r for the changing radius, I'm going to substitute little d. And the last thing we might want in here is a theta value that'll complete the right triangle that we're using. dq is the infinitesimal charge that is present on each ring segment, and because every point of charge on that ring segment is the same distance from the point in space where we're trying to measure, then I can treat that ring as a point charge, at least initially. That's going to change a little bit as we start incorporating information about how the charge is spread out in the system. We do need to know how the charge is spread out over that disk, and so we will substitute dq for sigma dA. This tells us that the charge is spread out uniformly over a surface area. And so now it looks like our integral needs to be set up with respect to the changing area of the disk. And that does make sense. We're going to have to add up all the infinitesimal surface areas of these rings. But how does the changing area of each ring change? Well, each one of those rings depends on the inner and the outer radius values that we've been using. And if we want to know the surface area that's made by a ring, we would solve for the surface area that is produced by the outer radius, and then we would subtract the surface area that is produced by the inner radius. And what's left over will be the surface area of that ring segment. So we need area of the outer ring segment, minus the area of the inner ring segment. And that will tell us what the infinitesimal area of that ring segment is going to be. Well, each radius is going to produce an area with respect to pi r squared. In this case, the outer radius is r dr. The inner radius is just r. So there's our infinitesimal area. We do need to expand this binomial. We have pi, and make sure you're expanding properly. Use your FOIL method. R squared plus 2r dr plus dr squared minus pi r squared equals dA. If this looks familiar, it's because we used this approach in deriving the electric field for a disk. And now we'll go through, we'll distribute the pi, and we can see that we have a pi r squared minus a pi r squared. Everything left is the infinitesimal area of our ring segment, except this is a second order differential. I don't want to be messing with that, especially considering the fact that I'm only going to be doing one round of integration. So I can't have a second order differential in there. But we had a way of getting around this before. If you remember, dr is infinitesimally small. It's approximately equal to 0, but nevertheless, it does need to be larger than 0. But if dr is approximately equal to 0, then what would dr squared be? Well, that would be even smaller. And so we're just going to say it's equal to 0. And we'll drop that last term. And that means that the infinitesimal surface area for each ring segment is 2 pi r dr. That is going to be plugged in to our integral expression. So now it would appear that our integration variable has switched to r. We're going to have sigma 4 pi epsilon 2 pi r dr over d. Let's make sure I got everything. Looks like I got everything in the right spot. I'll go ahead and integrate the left side just to get that out of the way. And any constants will pull out to the front. The 2 pi and the 4 pi are going to reduce, and we're left with sigma 2 epsilon naught integral r dr over d. Now, why did I leave little d in there? Well, if I travel back and forth along the radial direction, as little r changes its value, little d will also change its value. So I need to substitute little d in terms of preferably r and one of the other two terms, preferably not another variable. So I want to replace it with something involving r and z, but that's just Pythagorean theorem. We'd have r squared z squared. So d is now equal to root r squared z squared. The limits for this side of the integration, since we're integrating with respect to r, we'll start from the center of the disk, move out to the full radius big R. And at this point, we're ready to integrate the right-hand side of the expression. This integral can be accomplished using a UDU substitution. If you want to, you can go through that as an independent exercise. But I'm going to go ahead and jump to the end result of the integral just to save us a bit of time. And so what we're going to get from this is sigma 2 epsilon naught. And then we're going to end up with root z squared r squared from 0 to r. When we evaluate that between our limits, we get sigma 2 epsilon We have root z squared big R squared minus root z squared plus 0 squared, which is just going to be z. And there we have it. We have the electric potential produced directly above the center of a uniformly charged disk. At this point, we can play the what if game again. So what if we let z go to 0? In that case, if z goes to 0, we would have potential equal to, see, if z go to 0 there, we go to 0 there, which means we just have an r. And so we would have sigma r over 2 epsilon naught. At this point, you can reintroduce the value of sigma. Now that we've integrated about the entire surface of this ring, we can plug in the total charge over the total area as our sigma value. So we have total charge over total surface area, which is pi r squared. We have the r from the numerator there. And so let's see here, r and r cancel. And we have something that is almost like the point charge expression, except we've got a 2 in the denominator instead of the 4. So that's kind of interesting. The other possibility, what would happen if we let r go to 0? So what would happen if we collapsed this expression down to a single point? So you would think in this case, if we collapsed it down to a single point, that everything should collapse down to a point charge. Well, in that case, what we end up with is we end up with a 0 over 0 relationship, and that may not be evident right away, but if we plug in 0 for r, then we end up with z squared root, which is just z, minus z, which is 0. And you think to yourself, well, okay, anything times 0 is 0, but remember what sigma is made of. Sigma is the total charge divided by the total area. And even though we still have a 0 up in the numerator from that parenthesis set, we now have a 0 squared in the denominator. And so we basically end up with pi 2 epsilon r, where if r still goes to 0, well, we now have an undefined statement. And that's not to say that an answer does not exist, it's just undefined for our purposes. Other things that we could try, we could try letting z go to infinity. If we do that, if z goes to infinity, then r basically doesn't matter. The value of r cancels out, and we end up with z minus z, or infinity minus infinity, which would be effectively 0. So in other words, you've gotten so far away from this disk that you can't register its value. Whereas if you let r go to infinity, then the value of z doesn't matter. Z might as well be 0. And now you have infinity minus something. Well, again, that something might as well be 0. And now you have sigma to epsilon times infinity, which is infinity. In other words, you've got an infinite sheet of infinite charge. It's going to produce an infinite amount of potential. But this isn't a very realistic situation. So in the real world, we're not going to have to worry about that. But this does bring about a warning that if you have a very, very, very large sheet of charge, it's going to produce a very, very large electric potential within the general vicinity. And as we get into the next chapter, remember this electric potential term that we've been discussing. Its more common name, voltage. Okay, so now you're talking about having a very, very, very large voltage value. And high voltage, you've all seen the danger signs. High voltage, stay away. So having a very large plate or sheet with a lot of charge on it can make for a very dangerous situation, because that potential, as we're going to find out, is going to relate to how easy it is for charge in the system to move, and that charge would love nothing more than to be able to spread itself out over another area, like your body. And as that charge spreads through your body, it can cause a lot of damage, possibly even death. So that's why they say stay away from the high voltage. All right, I'm actually running a little low on time right now, so I'm gonna end this video here. But actually, I think this is a good point to stop. So if we need a fifth video for this chapter, so be it. It's better to go through this step by step and actually understand what's happening than to try and rush through it just for the sake of getting through the material. So we'll end things there. We've seen the ring. We've seen the disc. As always, you are not expected to reproduce the derivations, but you are expected to work with the end results, and if necessary, go in and play with those end results. Play the what-if game. See what happens when you take these expressions to different extremes. And then we'll apply that to the homework and the quizzes and the tests. So, see you at video 5.